So in this beam, this is again two span beam. You're gonna have here tension at the bottom, which means positive moment. And when tension becomes here on the top, it becomes negative moment. So in here, I'm gonna have a negative moment. This makes sense as well. I'm gonna put some reinforcing, and the reinforcing I'm gonna put it like this. I'm gonna say, well, let me put the reinforcing here. This reinforcing is gonna be good when come to the tension, and this span is gonna be resisting it, and here also is gonna be resisting the tension force. But also on the top, I need to add some rebars. So I'm gonna put it right here, right? So this rebar is gonna be taking the negative moment. Some people is gonna come and say, at this section of positive moment, you have tension rebar, and on the top is gonna be compression rebar. You can say, yeah, this makes sense. Here's my reason. In the top here, I'm gonna have compression. Also in here, I'm gonna have also compression in this side. And in the middle, at the bottom, at the support, I'm gonna have also some compression. So right here at this section, I'm gonna have tension reinforcing, compression reinforcement. And this section is gonna be exactly the same, tension and compression reinforcement. Also in this section, if you cut the section right here at the face of support, right? You're gonna say, I have here tension reinforcing, compression reinforcing. So compression reinforcing in most beams is gonna be there. And the question is, do you wanna really consider it or do you wanna ignore it in your design? I'm talking about actual practice. So in real practice, I can decide if I'd like to neglect or consider the compression reinforcing. In most cases, usually at the beginning, the first round of our design, we just ignore the compression reinforcing. We do it as single reinforcing or singly reinforced beam. And then we look at the demand and then we decide, do I need to use this additional, let's say 10% or 20% that I can gain from the compression reinforcing to my design or not? My design is tight, which means the demand is very close to the capacity, or it's not working. It is off by, let's say, 2-3%. And I don't want to add more tension reinforcing. So in this case, I'm going to be saying, let me look again at this beam and consider compression reinforcing and see if the beam is good without adding more reinforcing in the tension side. So I guess here I'm telling you the reason or usually the cases at which we're going to be using the compression reinforcing in our analysis. This is going to be in real practice. And of course, first you try to make it work without adding the compression reinforcing into the picture, into your analysis. But you know, compression reinforcing is going to be there in most cases because you need to have it as hangers. Can I show you here a little bit of the video? This just picture of the video that we've just started. This gonna be like the tension reinforcing because the three bars we're gonna put upside down, and this gonna be the compression reinforcing the top. Sometimes you also call this hanger bars. So this hanger bars is gonna be there because you need them to attach or to anchor these ties around them on the top. Don't forget, this gonna be the top, this gonna be the bottom. So they're gonna be there anyways. So in actual practice, first you ignore them. You say, let me just ignore them for now and let me look at demand versus capacity. Demand means how much moment you want the beam to support versus what capacity would you get out of these two rebars. If you're not happy with it and you'd like to increase it a little bit, then you start to use the help of these two rebars. If you're still not happy, you start to add a third rebar or a fourth and you change your design. Now, this is when it comes to actual practice, but when it comes to this course and to your exam or homework, I'm going to be very specific. Do I need to consider the compression reinforcing or not? All right. Did they answer the question?
Yeah, thank you very much.
All right, no problem.
Yeah, it makes more sense.
All right. Now, I'd like to understand here the performance of a beam when it comes to flexure versus shear. To understand it, we need to test some beams. So we're going to bring the beam, load it some way. I'm going to show you now the loading. And then we're going to be observing the cracks. When you load the beam, you're not going to be going to the maximum load that the beam can support. So I know, let's say this beam can support 100 kips as a load. I'm not going to apply the 100 kips. Now try first 5 kips, and then make it 10 kips, 15, 20, 25, so forth, till failure is going to happen of this beam. We call this kind of incremental loading, if you like. You can call it this way, because you'd like to see how the beam is going to be performed under this load. To understand the shear controlled beams versus flexure controlled beams, we need to change a little bit in the beam. For example, I'd like to test here the beam in flexure, which means a moment. So in this case, I need to be sure that the beam will never fail in shear. So I want it to be very strong in shear, so I can test the flexure failure. Because at the end, when you load it, you have this incremental loading. At the end, you want to see some failure of the beam to study the performance of this beam. So first, you're going to say, let me make it very strong in shear so that no failure is going to happen in shear. It's going to be only happening in flexure, in moment. But if you like to test the beam in shear, you'd like to see how the shear failure is going to look like and the shear cracks. In this case, you make it very strong in flexure. So you're going to be able to test the shear. Does it make sense? No? Yes?
Yes.
Okay, great. So this beam that you're looking at is going to be tested in flexure. Let me write here for you. The beam is going to get built. Here's the tension rebars, compression rebars going to be at the bottom. And you see how the tie is going to look like. It has a couple of hooks. We call this 135-degree hook. Here's the rebar. It goes here 135 degrees. This give you the top rebars, give you the bottom rebars once you put it upside down. Concrete mix, test, slump test. They put the beam, which means the reinforcing, in the form. They put the rebars, they start the vibration. Vibrate just to be sure that there is no voids inside. Here's the loading. The way that we're going to be loading this, here's a beam, support, and 2-point loads. So this big point load are going to have half of it is going to be in this side and half of it is going to be in this side. When you do this, you're going to be obtaining here a section of the beam. It's going to be only under moment, under flexure, and no shear. If you recall the shear diagram for something like this, you're going to have shear diagram is going to be going up here, straight, coming down, 0 in this side, going down, straight, going up. But when you look at the moment, it's going to look like trapezoidal. So this section of the beam is going to be only under flexure. So the effect of the shear is not going to be great in this section here. It's going to be only exposed to bending moment. Here is the actual beam, 2-point load, and then you have the supports, one at each end. And this point load is actually a hydraulic jack that they are pumping oil through it. And once they pump an oil through it, it's going to be pushing this piston down and apply the load. Now this section between the 2-point load is going to be free of shear because no shear here force is going to be in this section of it. And to measure out the load, they're going to have something called here load cell, something to measure the load. The bottom, of course, they measure the displacement or deformation. He's pumping the oil, putting some force, and look what happened. Just look at the cracks. Supposed to be flexure cracks. The cracks, of course, is going to be at the bottom of the beam. I guess you guys start to see it, right? Here are the cracks. The cracks start at the bottom of the beam and going to start to grow up. See the cracks? This is a section of maximum moment between these 2 points. So look at the cracks. It's going to start to develop and going up. Therefore, the neutral axis is going to be right here, right? Neutral axis is here, 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 here. You see the neutral axis dropping down because also the moment value is dropping down. And here there is no flexure cracks because the moment is very small. Let's continue loading and look at the crack propagation. See the crack becomes very visible. What happened? This is all flexure cracks. the longest crack or tallest crack is gonna be right at the maximum bending moment. And this all flexure cracks. There's no shear cracks here. It's coming from the bottom, going up. It's gonna start to go up and up again. At the end of the beam, the cracks are much smaller because the moment is much lower. And of course, you can observe here some deflection. It's coming down a little bit. Lots of cracks. Deflection is very clear. I guess if you see a beam like this, and let's say in a building, and you see all of these cracks and this deflection, you need to get out. So this is not brittle failure, because I've seen cracks, I've seen also deflection. See how much cracks? The rebars is under high tension force. You see at the bottom, at the end here at the bottom, there's no cracks because there is no moment. And this, all of these cracks is gonna be flexure cracks. More pumping, which means more force, vertical force. It's coming down. Expected to fail at any point. Now you have high strain at the bottom steel. The strain are getting very high. And the steel here is close to failure. Failure of the steel is going to be cutting the rebar. All of these cracks, see what happened? I stopped at the right moment. The steel snapped. We just cut right here because it reaches the highest strain. The strain is going to be excessive and the steel cannot take this strain anymore. So the beam is just going to collapse this way. And all of this is going to be all flexure cracks, and this is going to be flexure failure. Because failure is due to flexure. It is not failure due to shear. The beam is gone. See the rebar? Can you guys see the rebar or no?
It looks separated.
Yes.
It is not there. I mean, the rebar is cut. There's only a little piece of it here and there, but the rebar is gone. See this? Rebar is not there. Just a very small piece of the rebar is shown here. I can just bring this back. Look at this. See this piece? Here's the rebar. It's continuous on the other side. We just extend the bar a lot. So, I mean, snap. And you see compression failure on the top at the same time with the tension failure. Beam is gone. No, the thing, there's some wires, yeah, in the back, yeah. All right, so now we have an idea about flexure performance of beams. Now I'd like to see shear performance. What's gonna happen? There is one last point here that I want to show you guys. What's gonna happen here for the load versus time over time, right? When you measure it in seconds versus the load, vertical load. What happened? Straight, which means elastic deformation, and then after that you're gonna have this load. It's not really increasing the same rate. It comes to a point that the strength is gonna be just gone. Now let's see what does it mean by shear failure. So this beam here is gonna be tested for shear. So what happened in shear failure? You are not gonna put any ties because ties also help in shear. You know, the vertical ties. And we're gonna put lots of bottom reinforcement. So the beam is gonna be extremely strong when it comes to flexure. So now we want to test it in shear. This crack, which is right in the middle here, you call this flexure crack. Flexure crack. This is gonna be flexure crack. Flexure crack, flexure crack. Usually the flexure crack is gonna be vertical crack. Once the crack is gonna start taking angle, I know now it's gonna be like shear crack. This is what we call here shear crack. Flexor crack, the failure of it is going to happen once the rebar is going to reach the maximum allowable strain or attainable strain, and then it's going to fail. And shear crack is going to be taking an angle. Let's see what's going to happen. You see lots of deformation? You see what happened? This here is going to be shear crack, shear failure.
One more time, please.
You don't have lots of excessive deformation in this case. Just this cracks, they mark it on it with a marker. They bring a marker. If you look closely, here's the original crack, right? And this is a marker right next to it, or a pencil. It should be a pencil or a marker that you come right next to the crack, and then you start to draw the crack or a line or a curve, just to be sure that you're going to be able to take a picture of it. Nothing more. So this dark line is a pencil, and then they start to put numbers next to it. This give you like the loading step. Increment 1, increment 2, so they know exactly where it happens. If you look at this beam here, they use certain lens. This is why you feel that the beam is going up here and going down here. Actually, the beam is almost flat. So you don't see here lots of deflection like inflection. The amount of deflection is going to be very small, and then all of a sudden you have the sudden failure, which is bad failure. This is going to be shear bad failure. Just too bad. You don't want a beam to fail this way.
This would also be brittle failure, right?
Yes, this is brittle failure. Shear failure is brittle failure. Absolutely. Meaning, if I see a beam and I see some hair crack here and not very extensive, right? Not very deep throughout the depth of the beam, just one small crack here at the bottom. So I know that I may have here some deformation due to flexure. But once I see a crack, like in this direction here, like coming in a line this way, close to the support, and then this side's gonna be coming this way, I know that this beam is really in bad shape and it needs to be fixed right away. Show another quick video. Here's a small beam. They're doing testing. Someone is taking pictures. And you see, you don't see here lots of deflection, but you see here some shear cracks. Look what happened. It's gonna be brittle failure. You don't see here lots of deflection in the beam unless the shear failure is gonna happen. It's gonna be taking place. Look what happened. What would you call this? Is this flexor crack or shear crack?
Shear.
This is gonna be shear crack, right? Flexor crack is gonna be from the bottom. It's gonna be very small going up. This way is gonna be vertical crack. What happened here? You don't see lots of deformation, right? It is not really deflected much. But the shear crack is very evident. I mean, it's very clear. There's almost no deformation, which means non-ductile. This is gonna be brittle. Someone's gonna say, but I see here very little deformation. Yes, but it is unlike the other deformation that you see in flexor or in ductile failure. See this? It's very clear that they have here big crack, shear crack. See the crack? You don't see lots of deformation. It's not really deflecting that much. Beam is gone in shear. Any comment on this? Yes, no?
So is that either like the source of or the result of too much tensile reinforcement and not enough shear, or just not enough shear reinforcement?
Because there's no shear reinforcement and they put lots of reinforcing in the flexor.
Got
So
it.
that the beam is going to fail first in shear. Here's one
And
of the
then-
pictures that we're just looking at. Yes, go ahead, please.
Yeah, since they have a lot of flexure reinforcement, that's the reason for not a lot of deflection or warning signs.
No, not allowing flexor failure first.
Oh, okay.
So this beam was weak in shear. So we have this design specific for our testing. Okay.
Yeah. And that flexure cracking allows the steel to take over with the tensile
What do you mean?
reinforcement.
Steel is
So like when you have the vertical cracks,
yes,
that's when the bottom of the beam isn't effective anymore with tensile stress, and then that's when the steel takes over the majority.
yeah, because the shear is going to happen in an early stage of loading.
Okay.
So that's why you don't have here lots of cracks, vertical cracks.
Yeah.
But let me here take this picture and just assume for a second what happened if I have here one flexor crack. Where's the direction of tension? Is it going to be like this and like this? Does it make sense? Because the tension is going to be perpendicular to the crack, correct? And this is true because the tension is going to be at the bottom on both sides. I cannot come here and say tension is going to be in this direction, right? It's going to be coming down. No, tension is not going to be in this way. When you have this bending, you're going to have here tension, tension, and on the top, you're going to have here compression, and here you're going to have compression, right? And this is the tension compression. This is going to be like the C force, this is going to be the T force that we used to work on. So in flexor, this is going to be the situation, right? You're going to have your tension, compression, and you'll note here that the tension force is going to be perpendicular to the crack. So, okay, this is good for flexor. So I need to try it. This is going to be like flexor case. This is going to be the flexor. How about in the shear case? I'm going to say, where is the direction for the shear crack? I'm going to say, this could be the main direction of the shear crack is about coming in this direction. And I see here that the angle is about maybe 45 degrees with this. Now, where's the tension direction? You see, tension direction here was perpendicular to the crack. So tension direction is going to be like this. Right? Tension is going to be like this. This makes sense because when you look back at the video and you look what happened at the end, if I jump here to the end of the video, look what happened. Tension is coming this way, another tension is coming this way. This is why the beam is falling this way. It's coming apart like this. When you also look at this, see where's the tension direction? It was in this way, right? That's why the beam opened up this way. But in flexor, it's completely different. Look at the direction of the tension, if I may show it here. The direction of the tension was in this way and that way, not even an angle. So the tension is going to be in the direction of the bottom reinforcing. You know that this is going to be flexor failure or flexor cracks like this, right? And no shear cracks. And in this case, it's going to be all shear cracks. But my understanding, the shear force itself is going to be in this direction, right? You know, when you look at the reaction, and if you want to draw the shear diagram, you go this way, right? Do it like this, like this, like this, right? Or you can flip it if you want to. It depends on the way that you're looking from. So we need to understand what happened in this beam in details and what happened in the other beam. You have here two components, as I said. You're gonna have the moment component and the shear component, right? Just give you the moment and the shear component. Both will be acting on the same beam. And failure may happen in the moment or the flexure, or it can happen in shear. If you make the beam very strong in moment, which means if you put lots of reinforcing here and you be sure that you have enough capacity, and you make it very strong in moment and very weak in shear. You're gonna say, what does it mean by weak in shear? I understand, make it strong in moment, put enough reinforcing. How do you want to make it weak in shear? Now we understand what does it mean by the shear failure and how to resist the shear, so that I can decide what does it mean by making the beam strong in moment and weak in shear. I'm gonna be making it strong in moment and weak in shear only for the sake of testing, just understand the performance. It doesn't mean that in real life I'm going to be designing a beam to be good in moment and bad in shear. This is not true. I want the beam to be good in moment and shear, but to study the effect of moment or shear and how to design it, how to reinforce for it, how to do the analysis, we need to study each one of this component separately. If you like to resist the shear, you put lots of ties. So look here at direction of moment, direction of tension. Here's direction of moment, it's going to give you tension in this way. Direction here of the shear is going to get you some component in that way. Not because the shear is vertical, because this is what I observed based on testing. So in this case, I can come back and then maybe put some reinforcing this way. Ties, this is what you call here the ties. It's going to be closely spaced. And all of these ties, they're going to help to bring the beam all together and reduce the shear effect on the beam. Or in other words, I'm going to be make it here strong in shear. So if I want to test the beam in moment, I'd make it very strong in shear by providing lots of ties. So no shear failure is going to happen before the flexure failure. Now, if you like to test it in shear, you're going to make it very strong in moment and flexure and remove all of these ties. Don't put them there, just for the sake of testing. And then you put this load, also you're going to see this failure. Now let's see what we have here in this slide set, right? Here's the beam that failed again in tension. And here's the tension direction. It's going to be very important that we understand the direction of tension here first. And to resist it, you put the bottom reinforce. This is going to be the beam that failed in shear. And direction tension was like this. And I can say roughly, this is here an angle of 45 degrees. So we call this shear cracks. So when you look at the beam, there's lots of cracks like this. I'm going to be calling this to be shear crack, which is this crack here. And this one, I'm going to be calling it a flexure crack. You can say, how about this piece? You can say, you know what? The first piece of it is going to be maybe flexure crack. It's going to be coming like this. And then after that, I'm going to have here a shear crack on an angle. It's going to be coming like this. Most likely, the shear crack is going to happen at the end, because here, usually you have high shear force. And most of the flexure crack is going to happen in the middle, because it's where you have the maximum moment. So let's say that you go to a site, to some structure, and then you look at the beam like this. What type of crack is this? Is this flexure crack? You look at this and say, this is going to be the support, right? You have here a wall that supports this beam. And you see the crack is happening at the end on an angle. What would you call this shear? Is this with this crack? Is this a shear crack or flexure crack?
Shear
This
crack.
is a shear crack. The bad thing about this crack, that's going to be causing brittle failure of the beam. You don't want this to happen. Generally speaking, you don't want a beam to fail or to collapse. But if you have an overload condition, which means someone starts here to put lots of loads beyond the design value by a lot. Let's say a mistake, someone misused the building. This building is designed to be residential, let's say, or an office. And then all of a sudden someone is using it for storage. He starts to put lots of weight on the top of the floor. It was just too much. He started to put lots of paper. You know, paper is very heavy. When you think about paper, let's say height of 5-6 feet, this can be too heavy. And they start to put equipment on the top that this floor is not designed for, and this beam is not designed for it. This is the case that we call overload, which means that you put load beyond your design values. Now, let's say in this case, some failure is going to happen. Which one do you prefer? Do you prefer flexor failure or shear failure? Which one would you like to happen? Is going to be flexor failure. What is the reason of this?
You actually get deformation.
Yeah, and the formation is going to do what? It's going to give you some warning. Yeah, exactly. It's going to take some time so that you can get out of there. This is why it's important that we said we prefer ductile failure and not brittle failure. Brittle failure is going to be just bad. It's going to be sudden. You're going to see lots of deformation before it happens. And don't forget, in most buildings, the whole thing here is going to be covered with ceiling. You're going to have a T-bar ceiling or something there. So when deflection is going to happen, you're going to see the T-bar ceiling coming down. But when shear cracks is going to happen, you're not going to see it. You may not be able to see it at all. It is going to be hidden and no deflection or deformation. You don't have here big deformation. So it's not going to be something that you'd like to see here. So if failure to happen, we'd like to see ductile failure. We don't want to see brittle failure due to shear. Now let's look here at this beam and see what's going to happen, how the shear diagram is going to look like. So I'm going to say if this beam is uniformly loaded, shear diagram, I'm going to go here with the reaction is going to be going up and then go down like this and go like this, right? This is going to be the shear diagram and this is going to be your datum is going to be right here in the middle. So the high shear is going to be in here and in here. So I'd like to take an element. If you remember Moore circle, if anyone remembers Moore circle and the combined stresses, going to be taking an element out of this beam at the end where the shear is going to be critical and just draw it here. This is going to be the same element. You just take it and put it right here in this place. On the left side of the element, you're going to have shear force going up. Look at this. The shear is going to be going up. And this side is going to be coming down, which means this side. When you have any shear happens like this, you need to have this conjugate shear happen at the same time to balance the stress element. So I'm going to be more interested in this component and this component. What is the combined effect of both of these two? When you have two forces, let's just forget about these two. You have one component coming this way, another component coming this way. It's going to give you a resultant like this. Same thing here. You're going to have a resultant coming this way. And this makes sense. Why? Because in a case like this, the crack is going to be coming this way. So now let's look. This is going to be the crack direction. And this is going to be the tension force on both sides. And this is what you call here diagonal tension. Why diagonal tension? Because it's going to be happening at an angle, and the crack is going to be looking this way. Look at the end of the beam. This is going to be the expected shear crack if some shear crack to happen. You're going to have tension this way and tension this way. What is this tension is about, or this diagonal tension? It's going to be coming from two components, the vertical component and the conjugate that goes with it. And this explains the type of shear, and also this exactly explains what I was talking here about. If you remember this picture, this give you the crack direction, and this give you the tension perpendicular to the crack. So now it makes sense. When I'm looking at this, I'm going to say, yes, crack direction is going to be about here, right? And the tension is going to be perpendicular to it. How to resist it again? You put ties, vertical ties. Now the strength of the concrete here and the steel, right? Here's how you put some ties. This ties is going to be intersecting with this surface, the failure surface. And the resistance of this two rebars that you're going to be cutting through, this is going to be one of them. And here's going to be the other one through the surface of the concrete. This is going to be the cross-section area of the steel resisting the shear. So it's not going to be this anymore, right? It's not going to be the bottom reinforcing. So let's say that this section here is going to be cut right here, right? So the cross-section area of the steel rebar resisting the shear is going to be this tie and this tie, which is these two cross-section areas. So for example, if I have number 3 rebar, so I'm gonna put here quick numerical example. I'm gonna say number 3 bars, 2 legs, right? What are the 2 legs? Here's one, here's the other one, 2 legs. Sometimes you can have a third one or a fourth one if you want to. How much is AS resisting the shear in this case? We're gonna call it here AV. V stands for the shear, right? You know, V usually used for the shear. Yes, it's gonna be equal to 2 legs in this case times. Can someone help me with the cross-section area of number 3? Rebar?
11.
Okay, good. All right. I'm gonna have 0.22 square inch. This is gonna be the cross-section area of the C resisting the shear in this case. It's gonna be a spacing of S. So if you want to make this stronger, you're gonna be going here with smaller spacing, right? So once you make it like a smaller spacing, the strength is gonna be higher. If you make this distance, the spacing between this 2 sets of ties, the strength and shear is gonna be lower. This has nothing to do with the flexure strength. The flexure strength, you're gonna be attaining it when you provide enough reinforcing bars at the bottom for tension, like these 2 rebars. Any questions?
So in the previous examples, when we talk about flexure, we would say putting too many bars was bad because it created a ductile failure. So in this case, if we add more ties, it would actually help prevent shear failure.
Yes, exactly. But it's gonna also go to a limit that once you start to add rebars, you're gonna be in trouble. It's not good because you'd like to see some concrete with the steel. And the code recognize this issue. I'm gonna show it to you very soon. Okay? All right. No problem. So yes, okay, now we added all of these ties. Now let's look here at the critical section of shear. Here's one beam to column connection, right? I know that I have here uniform load coming from this way and uniform load coming here from this way. Same thing here in this beam. Here's the uniform load. It's gonna be coming throughout the entire beam. And in this case, I have uniform load plus this point load. This is gonna be another case, right? I have here 4 cases that I'd like to study. Same thing here. I'm gonna have here uniform load. If I may take you back here to one of these beams. Let's say this beam here. See, here's a column, and the column has a width, right? Like in here. The column is gonna be that wide. And let's say that I'm gonna be using the same shear diagram that you're looking at. And here's a column. You just draw the column this way. Let's get closer here. Would you design this beam for this amount of shear from here to there, or only this shear from here to there? Which value would you use? Don't forget that this is gonna be a solid column. This is gonna be continuous. I'd like to hear from you.
From the max amount, no?
Yeah, say this is gonna be V1, which is right at the support. And the other value is gonna be this V2. You see this value here? Say from here to there, this is gonna be V2. Where's V2? It's gonna be this ordinate here, from this point to that point. This is gonna be V2. V1 is gonna be from here to there. Now, you need to understand that this V1 is resisted by the entire depth of the column. It's just going directly through the column. So if this shear is unrealistic here, this doesn't make any sense. And the amount of shear that this beam, now where's the beam now? The section of the beam is gonna start right here at this place, right? So the depth of this beam is what's resisting V2. But the depth of this column, which means the column height, is gonna be resisting V1. So actually, if you like to check the beam itself, you need to take this V2, you need to go to the face of support. We call this the face of support. Now, where's support? It's gonna be the column. Face of support is gonna be right here, which means the shear value. Does it make sense? Okay. Also, we'd like to see what's gonna happen if this beam to fail. So we're gonna say, let's look here at this beam and say, failure to happen, what's gonna happen here? I'm gonna say, what's gonna happen? This part of the beam is gonna be coming down like this. This side is gonna be coming this way, right? It's gonna be coming like this. Which means this section of the column, if I may draw it here, I'll draw this column like this. And this beam is gonna be from the other side. So if you start to load this a lot, the beam is gonna be collapsing this way, and from this side also is gonna be collapsing this way. This means the critical shear was not really at face of support. It happened in an angle. You know, when the failure is gonna happen, failure is gonna be happening in an angle, the 45 degrees that we're talking about. And we have drawn it. Let's look here at this location. You see where the shear happens? It doesn't happen at the face of support. Now where support is gonna be the support, face of support is gonna be right here, right? It's gonna be this line. So actually shear doesn't happen at face of support. Let me write this down here. This is gonna be face of support. And instead of happening at a little bit away from face of support, because this piece is gonna be working as integral part of the support of the column. And I'm sure that you guys have seen this here, right? The failure. You see this piece? It works as if this piece is part of the support. Now let me look here at this diagram. This piece here is gonna work as integral part of the column. And the beam is gonna be feeling right at this point. So what the code says, don't take the shear at face of support, don't take it to the center line, take it at d distance away from face of support. Why d distance? Because this distance from here to there is called d. It's gonna be the d distance, right? Roughly. I know someone's gonna say h versus d. I'm gonna say, not big deal. So if you go here 45 degrees, and this is gonna be called d, this also is gonna be called d distance. So from here to there, just to be accurate according to this drawing, this is gonna be your d distance. You see, this is gonna be here your d distance, which I have it here written in black, if you see this. Which means this part about d distance of the column, right, of this beam, this portion of the beam is gonna be acting as part of the column. And the beam is gonna be collapsing this way. So the beam originally was right here. When you load it, when shear failure happened, this is gonna start to come down this way. So what the code says, when you take here the shear, don't take it at face of support. Take it at d distance away from face of support. Therefore, if you like here to see the amount of shear that you need to design for, you're not gonna be designing for V1 or V2. Actually, what you need to do is to go at about d distance away from face of support and take the shear at this location, which is gonna be V3. It's gonna be reduced amount of shear. Where is this from to? Yes, say it's gonna be this value from here all the way to here. So this line here indicates the amount of shear that you need to design for. So you don't really need to design for the reaction. You don't need to take it to face of support. You're gonna be taking a d distance away from face of support, and then find out the shear from your diagram, and then use in your design. What would you call the shear here? Is this demand or capacity? I'm gonna say, of course, this is gonna be demand. When you draw here the diagram, it's gonna be your demand, right? It's gonna be V sub U. So I'm gonna go here to this. I'm gonna say what we are talking about here is gonna be V sub U. It's gonna be the demand. The code comes here and say, if you have one of these cases, right? Here's the first case that I'd like to look at. They call this monolithic, which means the column and the beams were poured in the same time. They're gonna be going away d distance from face of the column or face of support. And here they say, well, in many cases, like in bridge construction, you're gonna have a pier like this. And it's gonna be the actual support. So when you go d distance, don't go d distance from here. They say this is incorrect. Don't go d from here. You need to go d from the actual, I'm gonna say here, interface between the column or the support to the beam. They also say, look at the failure in a case like that. I understand in this case, when the failure is gonna happen, it's gonna happen like this. Here's the failure, right? Yes, it's gonna happen like this. Beam is gonna be falling, and this part is gonna be working as part of the column. But how about here? Do you expect I'm gonna have something like this, similar to the other one on the top? You think we may have anything like this? You think about this. So let's assume for a second that this is true. Now try to take this and push it down. You cannot, because it's gonna be working here as a ledge, right? This will never happen. So your chance for the shear to happen here, if you have a flat face like this and a flat face like this, so the beam is gonna be sliding down like this, right? So in a case like this, the code says when the support is gonna be upturned, which means like in this case, right? And the support is gonna be taking tension. You take the shear at the face of support. So in here, you take the shear at d distance from the actual support at face of support. Also, to give you another case, they said if you have a point load within d distance, nothing like this is gonna happen. This will never happen, because look what happened here. If I may put this back, I'm gonna be taking this d out. If your point load is gonna be right here, would this piece come down this way, or the whole thing is gonna be coming down? You're gonna break this piece, right? So in a case like this, you're gonna be taking the shear at the face of support. Any questions?
Yeah, that last thing you mentioned with the point load on the top.
Here, yes.
The one up, yeah. If we place that right there,
Yeah.
The point load wouldn't be taken by the compression zone.
This is now about the shear, right? It's not about the flexure. When you have flexure, you're gonna say compression and tension. But this shear here, it wants to break this vertically. It wants to cut it off this way. It's not gonna be causing, when you say tension compression, you're gonna say, I have rebars here, right? But this is actually gonna be negative moment, which means tension is gonna be in the top and compression is gonna be here. And this here is gonna be going out of the picture because the shear. So the shear is gonna be breaking this piece off like this.
And that shear is that's caused by the self weight of the beam itself?
The self weight and the life load and any point load, all the loads come from above.
Got it.
You know, when you do this V sub U, you're going to be doing this load combinations, right? So this load combination shows where the shear source is going to be coming from. Like, for example, when you have dead load and then you have life load, if you remember this 1.4 dead versus 1.2 dead plus 1.6 life, right? So you need to do the same thing, but in this case, it's going to be about the shear, not about the moment.
Yeah.
Right? Okay. Good. All right. Now we understand the demand. So the shear demand, we discussed it, and then now we know whenever we have a beam and we have columns, we need to consider the d distance away from face of support. So in our case, in our concrete design project, in a case like this, you're going to be having that face of support. So okay. Let's do also this load combinations again. With that, I have the shear demand. Now the strength. Now you have the demand, which means how much force you want to support. Now we're looking at the strength of this beam. The strength is coming from two components. The concrete by itself, it has a strength, and the reinforcing bars that you put as ties, if you recall the ties thing that we were talking about, these ties, it's going to also have some strength. So you have the phi factor, phi Vn is going to be the strength, also like what we have here, phi Vn is going to be the strength. Vn is going to be the shear nominal strength, very similar to the moment. We have the nominal moment capacity, and then we have the moment capacity. Here we have also nominal shear strength or capacity, and then you have the capacity once you apply the phi factor. The simple thing about this equation here, that the phi factor is equal to 0.75, there is no chart for it. You just take it as is. Whenever that you have shear design, you don't really play with it. There is no 0.6 versus 0.9 or 0.65. It's all 0.75. And then you're going to have some strengths coming from the concrete and another component coming from the reinforcing bars. Which reinforcing bars? This is going to be the ties, not the bottom rebars, right? You just add them to each other, multiply by phi factor, the 0.75. It's going to be phi Vn. in your design, you need to compare this VVN with V sub U. It needs to be greater than V sub U, your demand. So V sub C is going to be the shear component by concrete, and VS component by reinforcement, which means the times. For the concrete, it's going to be one simple equation. You don't have here lots of analysis like whenever you had that, like the rectangular section with single reinforcing or double reinforcing. We don't have all of that. And instead, what we have, V sub C, the strength of the concrete, is going to be equal to what? 2 times the square root of F prime C. And this has to be in PSI, right? You remember this? This is going to be a PSI code, especially when you see a situation like this. Let's say in this case, this is going to be F prime C, is going to be in PSI. Multiplied by the width of the beam width, multiplied by the depth of the beam. Meaning, if I have a T section, I'm not going to be using here B, right? I cannot use B, which is the flange width. I'm going to be using the web width. Let me give you this for quick. B is going to be the width of the web at the bottom, not this, even if you have a T section. And with that, you're going to have here the concrete strength. Any questions with this?
If you have a T section that has a wider bottom than top.
You're going to be taking the web. So let's say your T section is going to be like this, right? Not perfect T, but this is what we have. Now, where's the web width? Is it going to be this guy or this guy? The web is going to be this one. It's going to be the smaller of the two.
Okay.
This is going to be standard in our shear design.
Okay.
Now, the answer in this case is going to be in pounds, because look at this. It's going to be like in PSI, pound per square inch. This is going to be an inch. So at the end, this is going to be in pounds. So at the end, you maybe need to divide this by 1,000 to put it in kips. So we're going to say pounds. Any questions?
Will, for shear strength, will phi always be 0.75 or will it vary?
This is going to be the phi factor. At the end, you need to multiply this by the phi factor, right?
Yeah, will it always be 0.75 when we're finding shear strength?
0.75, this is going to be strength reduction factor, right?
Yeah.
Which means that you take this after you are done with this, multiply by this number, VC, by 0.75.
Oh, but I mean, like, will it vary like when we find
Vary meaning what? Vary why? The phi factor is only one value.
okay.
Are you talking about the phi factor value, or are you talking about the total shear strength value?
No, the phi factor value.
No,
Like,
the
are we
phi
always
factor,
gonna use that one?
yeah. No, the phi factor is just one value. It doesn't change. For shear, it's going to be equal to 0.75. Just one value.
Got it.
There is no diagram for it. You know, like in the past, we used to have this diagram.
Yeah, that
Okay.
was what I was wondering about.
Yeah. No.
Cool. Thank you.
All right. So it's easier, right?
Yeah.
This is what you care about.
Yep.
All right. Give me a second here. Okay. The maximum square root of F prime C is going to be 100 psi. The meaning of that means the maximum concrete strength that you can use in this equation is going to be 10,000 psi. If it is more than 10,000 psi, this square root of F prime C is going to remain as 100. 10,000 square root of 10,000 is going to be 100, right? Okay. Any questions? Are we good? Yes? No?
Yes.
Okay. I'm gonna stop at this point because this section here is gonna be about the steel, and then we need to do an example, right? On this. What's important about this example that now I'd like to bring to your attention before we come next time is going to be this shear diagram. Here's the shear diagram that you draw. Here's going to be the support, right? The reaction, reaction, reaction. Here's the column. The column width or length is going to be from here to there, right? It's going to be given to you. As is here, the column length is how much? Can someone help me here with this? How much is this column width? From here to there, roughly, without looking at any writing. It says from the face of the column to the center of the support is going to be a foot. Therefore, this is about 2 feet.
12 inches.
2 feet.
Yeah, 2 feet. From here to there is a foot, and from here to there is going to be a foot. And the depth given here 13.5 inch. So if you want to find out the shear that you can use in your design, is going to be actually at the distance away from face of support. And according to the shear diagram, you have here, let's say 32 kips to be the reaction, right? You're going to be using at the end 25.9. It's going to be reduced. Why? Because the code says it's okay to take the shear at face of support. You go here at the distance, you figure out the exact location, and then you measure the shear here, you figure out the shear value from your analysis. This span of any beam, when someone's going to say the beam span is going to be from center line to center line of support to center line of support. We call this the clear span. Yes, say this one here, we call it the span, or we call it center line to center line span. It's the same thing. So both of these two terms mean the same. If you just say span, it means center line to center line, or you can call center line to center line span. And this one here, we call clear span. So what's the clear span? The clear span is going to be from face of support to face of support, face of column to face of column. It's going to be this distance from here to there. We call this the clear span. It's going to be this distance here. Now, where's the center line to center line span? It's going to be from here, center of the column to center of the column. So you guys understand difference in definition, right? This is going to be the center line to center line span, and this is going to be your clear span, which is from here to there. Are we good? Questions before I let you go?
Good.
I had one question on the submittal too.
Yes.
The H 20 inches, that will be below the slab, or will it include the slab thickness?
Did we talk about this last time? I don't recall. Yes or no? Anyone can help me here? Can you guys help?
I don't remember.
All right, so let's read it together. Let's see what it says. Okay, here's the information provided. It says beam total depth. What's the beam total depth? H.
That's including part of the slab, or the slab, right?
Here's a discussion that we went through last time about this issue. I said the beam depth given to you, H, is going to be from here to there. It is not from here to there. So this includes the slab thickness, right? So when I look here at any T section like this, where's the 20 inches? I'm going to say 20 inches is going to be from here to there. What does he call it? They call this H. Do I have any proof or any evidence to support here my suggestion that this is going to be the total, this is going to be the total, right? Depth, here's D, here's H. I'm going to say, well, I'm not sure. So what should I do now if I don't have someone to help me on this? I'm going to be
Since it's
looking at
all-
this. I'm going to be looking at some example. Just go through the slides. Where is D now? D from where to where? It's clear. Depth of the beam, top compression to the rebars. Let me look for another one. Here's D. What do you call this? The 12 inch. D. Okay, same thing. Here's the D distance. Even in my analysis here, I said D, right? I use D minus A over 2. Here it is, right? D minus 2 divided by 2. Which one is this? I'm going to say 12 minus 2 divided by 2. ZF is D minus A over 2 minus the step thickness divided by 2. So now I understand the D distance, right? How much is H here? It's going to be 27 inch, and D is going to be 24 inch. Now let me go back to this guy. Beam total depth, 20. Now you know where is this measure from. Beam depth. It's not beam depth. It should be beam depth. So. All right, I need to correct that.
I like being that better.
Okay, I'll keep it for you. All right. So
All right,
the
thank
beam
you.
depth, no problem. So the beam depth here is going to be from the top compression all the way to the tension rebars. Good question. I'm sure that maybe someone else has the same question with you, but all right. Any more questions before we go? All right, go ahead, please, and find out.